Okay, D1, electric field strength. A charge Q1, so we're going to do like we always do for every problem. We're going to write down our given, and we're going to write what we want to find, we're going to draw a diagram, etc. So it says a charge Q1, so Q1 is equal to 5 microcoulombs, is at the origin. That means I'm going to have to draw a picture. A second charge Q2, which is negative 3 microcoulombs, is on the x-axis at point 8. Now what I should have done, and I'll do it right now, is I need to change this microcoulombs because there's a prefix, so 5 times 10 to the negative 6 coulombs. And then Q2 would be negative 3 times 10 to the negative 6 coulombs. All right, so the next thing I'm going to do is I'm going to draw my picture. So this represents, this is X, this is Y, and it tells me that the first one is at the origin, so this is my positive charge, and this is Q1. They tell me the other one is 0.8 meters away, so I'm going to draw it over here. That's negative. This is Q2. What I know is the distance between these two is equal to 0.8 meters. Find the electric field at a point on the y-axis 0.5 meters from the origin. So now what I want to do is I want to find the electric field up here, which this distance here is 0.5 meters. So I'm going to call this point P, because that's the point where I want to find the electric field at that point. Now, before I start plugging numbers in or doing anything else, I need to draw a picture of what my electric field looks like. Okay? So at this point here, there's going to be an electric field from this charge on this point. Now, forget about this one. The electric field, which way does the electric field point for a positive charge? Does it point out or in? Out. So this field is going to go up this way. So I'm going to call this E1 because it's pointing out of the positive charge. Remember, I want to find the electric field at this point P. So I have to see what influence does this positive charge have on that point. Now I want to find the electric field because of this negative charge. So which way is the electric field going to point in terms of the negative charge? In. It's going to point towards it. So what I'm going to do is, and I'll just grab my ruler real quick. Didn't have it ready. And it is going to, now that's not the field, I'm just drawing the pencil. So my electric field, I'm going to call it E2, and do you see how it's going to point towards Q2? So now I have my electric fields. I have E1 and E2. Remember, the electric field strength, that is a vector quantity. It has both magnitude and direction. So in order to find E, I have to add up E1 and E2. Now, there's only two forces. You could add them head to tail and find the resultant. It's not going to be a right triangle. So unless you know law of cosines and law of sines, that would be the only way to find the strength. But we'll just do it the same way that we've done it before. Okay? So what should I do first? Well, first, what I'm going to do is I'm going to calculate E1 and E2. So E1 is going to be K Q1 over R1 squared. So that's going to be 9 times 10 to the 9 Newton meter squared per Coulomb squared times 5 times 10 to the negative 6 coulombs divided by 0.5 meters squared. So when I put that in my calculator, 5, remember we have to know how to use our exponent buttons, 5 EE6 minus times 9 EE9 equals divided by 0.5 squared equals. Second psi, so when I do that, it comes out to be 1.8 times 10 to the 5th newtons per coulomb. So that's E1. E2 is equal to KQ2 over R2 squared. Now remember, here's my R is the distance from here to here. What is this distance? Do I know what this distance R2 is? Do they give me the distance from here to here? No. But what do they give me? Is this a right triangle? Yeah. What would I use to find out this distance? I would use the Pythagorean theorem. Now I could do it separately, but that's so easy. I'm just going to incorporate it in here. So I'm going to say 9 times 10 to the 9 Newton meter squared per Coulomb squared times negative 3 times 10 to the negative 6 coulombs divided by, and I don't know what that distance is, but I know I can use the Pythagorean theorem, which would be the square root of 0.5 squared plus 0.8 squared. So I'm just going to write all that here. I'm going to do the square root of 0.5 squared plus 0.8 squared, and that whole quantity is squared. Now if you want to do the Pythagorean theorem separately and calculate what R2 is, go ahead and do it. Okay? So when I do all that, E2 comes out to be negative 3.06 times 10 to the 4 newtons per coulomb. Okay, now comes to be chart time. So on my chart, I'm going to have E. Then I'm going to have E1. Then I'm going to have E2. And then I'm going to have E total. Then I'm going to have the X component. And then I'm going to have the Y component. All right, now let's just look at E1. Here's E1. Now, if I redraw it, this is what E1 looks like. Does E1 have an X component? Does E1 have an X component? No, it's going straight up, so I know this is 0. And then the Y component is the magnitude of that, so it's positive 1.8 times 10 to the 5 newtons per coulomb. Okay, now I'm going to draw E2 just the way I see it. This is E2. So now I want to find E2x and E2y. This is where I start. This is where I end. From one vector, from the head of one, I do the tail of the other. So this is E2y, and this is going to be E2x. Now, if I use definition of sine, cosine, and tangent, I don't know any of the angles, so what I could do is I can go back up here. I'll just figure out this angle because it's so easy. So I'm going to say tan of theta is equal to opposite over adjacent. Now, if I figured out what the hypotenuse is, I could use it, but I'll just do this. So tan of theta is equal to 0.5 over 0.8. I'm using this triangle just to find that angle in a triangle. So theta comes out to be 32 degrees. So this angle here is 32. So now when I come back here, remember, all I'm doing here, I'm not doing any new physics. The only new physics I learned today is this right here, that E is equal to KQ over R. That is the only new thing that we learned today. Okay? So now I can say E2x is equal to E2 times the cosine of 32 degrees. So I would go on my calculator and figure that out. So that comes out to be 2.6 times 10 to the 4 Newton per Coulomb. And then E2y is going to be E2 sine of 32 degrees, which would be negative 1.6 times 10 to the 4 newtons per Coulomb. So now I'm going to put that in my chart. So E2x is going to be positive 2.6 times 10 to the 4, and this is going to be negative 1.6 times 10 to the 4. Whoops. It's a 1. Now, some of you are probably like, where did she get the sine and the cosine from? I don't know where that came from. Where did she get that? How'd she know what to do? Okay? Sometimes, because we've been doing this all year over and over and over again. I have a triangle. This is E2, which I know. That's the hypotenuse. This angle here, I just figured out, was 32 degrees. It's a right triangle. So if you need to write out your definitions and say, oh, sine of theta is equal to opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. This is E2. This is E2x and E2y. So if you need to, then look at this and say, well, cosine of theta is equal to adjacent, E2x, over the hypotenuse, E2. And then rearrange this and multiply this. E2 cosine theta is equal to E2x. So that's where I got this from. Because we've been doing this since the beginning of the school year. Today I'm trying to teach you about electric fields. I'm not going back to day one saying, okay, vectors are added, we're doing this is vector resolution, and we're finding one of the sides of the triangle. This is not physics. This is math. So that's where these came from. Okay? So if you cannot look at the triangle and you want to just start from scratch and say, well, I know sine's opposite over hypotenuse, cosine's adjacent over hypotenuse, here's my triangle, here's my variables, and do it step by step by step so you don't make a mistake, that's fine. Okay? All right, let's get back to the problem. So now I'm going to add these up. So I'm going to add these. It's going to be 2.6 times 10 to the 4. And then this one comes out to be, this is positive and that's negative, so it's 1.64 times 10 to the 5 Newton per Coulomb. So now this is E total x, and this is E total y. You don't have to call it total. It's just, I know when I did something else, some of you were confused. So now, this is positive x, so I just pick a starting point. Here's my starting point. So this is positive. I'm going to use my same standard Cartesian sign convention. Up and to the right is positive, so this is positive, so I'm going to make it go to the right. So this is my E total x. E total y is also positive. From the head of that vector, I do the tail of the other. This is E total y. From where I start to where I end up, I do my resultant. This is E total. And then I need to have a direction. So to find E total, I use the Pythagorean theorem. And that's going to be the square root of ETX squared plus ETY squared. I substitute in my values, which would be 2.6 times 10 to the 4 squared plus 1.6 times 10 to the 5 squared. So when I do that, it comes out to be 1.66 times 10 to the 5 newtons per coulomb. But that's not my final answer, because vectors have both magnitude and direction. So now, to find this angle, I have opposite and adjacent, which means I can use tangent. So tan of theta is equal to opposite over adjacent. So ETY over ETX. So 1.64 times 10 to the 5 over 2.6 times 10 to the 4. So I put that in my calculator. 1.64 EE5 divided by 2.6 EE4 equals. But that just doesn't give me the angle, so then I have to press second tan, and my angle comes out to be 81 degrees. So my final answer is going to be 1.66 times 10 to the 5 newtons per coulomb. And because this is pointing up, remember this is our x and y axis, so it's 81 degrees above the positive x-axis. So that's my final answer with both magnitude and with the direction. And that's it.